From the subatomic to the solar system, from our planet to the depths of the cosmos, the same elements are scattered through the stars, through every galaxy. Common matter forms everything, and all of us. Once this profusion and confusion did not exist. There was nothing. No matter, no radiation, no space, no time. Some reject the theory, but most cosmologists agree the universe was born of a Big Bang. But while they can explain how, they have no idea why. From the Big Bang, from an infinitesimal speck, the universe exploded. Not into space, because there was none, but inflating within itself. Today that expansion continues, the space between galaxies ever widening. The Big Bang was some 14 billion years ago. In the first trillionth of a second, time, space, and matter grew 100 million times to less than the size of an atom. Then, in another instant, and more dramatically, they were as big as a galaxy. The universe was a soup, so hot that energy generated matter and antimatter as massive particles. As they decayed into lighter ones, matter triumphed over antimatter by 1 part in a billion, but enough to yield us the cosmos. By now, the temperature had dropped to 1 trillion degrees Celsius. When the era ended, the universe was just 10 millionths of a second old. Physicists simulate that era with an atom smasher. 2 rings accelerate particles, called heavy ions, in opposite directions. At intersections, close to the speed of light, beams of ions collide with tremendous energy. They produce showers of subatomic particles. The accelerator at America's Brookhaven National Laboratory is 4 kilometers round. Within, for an instant, a curtain lifts on the embryonic universe. We're in a plasma of subatomic particles, of quarks and gluons. At 1,000th of a second after the Big Bang, quarks and gluons were forming protons and neutrons. Then at 1 second, and down to 1 billion degrees, protons and neutrons were making atomic nuclei. At 3 minutes came the first elements, hydrogen, helium, and a little lithium. Electrons, here in blue, were tamed during the next 350,000 years, captured in closed orbits around nuclei. Temperature was down to 3,000 degrees. When electrons were locked into atoms, they no longer blocked the passage of light-bearing photons. All of a sudden, the fog cleared. The universe became transparent. And so began the matter-dominated era. From clouds of hydrogen and helium gas formed galaxies. Galaxies formed clusters, and clusters formed filaments. It goes on to this day, ever expanding, ever cooling. This expansion is the prime evidence for the Big Bang. But there's more. From 350,000 years after the Big Bang, when the cosmos became visible. It's called cosmic background radiation, and it pervades the universe. In 1965, it was discovered by accident as a faint microwave hiss. This antenna picked it up from every direction in the sky. From near infinite heat, the universe had cooled to 3,000 degrees when the radiation was emitted. It originated as ultraviolet radiation, but shifted to microwave as the universe expanded and cooled. Today, the cosmic temperature is just under minus 270 degrees. In 1992, COBE, the Cosmic Background Explorer, was the first to make sense of the microwave hiss. COBE took the temperature of the entire sky. Different colors were fluctuations of a few millionths of a degree. This launch in 2001 brought COBE measurements into sharper focus. The probe, known as WMAP, orbited around nothing. It wobbled because of the pull of the planets. At 1.5 million kilometers out, WMAP was free of microwaves and magnetic interference from Earth. From its stable thermal environment, the probe worked with its back to the Sun, the Earth, and the Moon. Results were remarkable. By eliminating the red band, the strong and superfluous signals of our galaxy, WMAP had charted the cosmos in microwaves, with new insight. On the left, compare Kobe's fuzzier map. Now with WMAP, observe the detail, see the ripples. Like a pebble in liquid, ripples on the left in oil differ from those on the right in water. The medium determines the ripples. And so do the number of pebbles, plus their size and mass. These ripples are like density variations in the early universe. Expansion from the Big Bang wasn't smooth. Matter rippled and clumped. WMAP's temperature chart revealed that clumping. Here were the seeds of the large-scale structure of the universe. The structure resolved within 1 billion years. Galaxies clustered along frothy filaments. Between them, voids of space ever widened. And stars were born. All over the universe, lights came on, as one astronomer put it. Everywhere, gas was condensing and heating to initiate nuclear fusion. This first generation of stars was hotter, brighter, and more massive than the supergiants of today. Now, generations later, galaxies swarm in superclusters where filaments intersect. This cellular structure was set by density fluctuations in the infant universe. Their detection was through cosmic background radiation. The 50 billion or so galaxies of the universe are its building blocks. Most galaxies are gregarious, from groups of a few dozen to clusters of thousands. Bound together by gravity, one of the most massive is this galaxy cluster. Here in simulation, the evolution of a cluster over 10 billion years. Galaxies collide and merge. Most astronomers believe clusters grew this way. Dwarf galaxies combining, larger galaxies clustering. Again in simulation, astronomers have built a picture of cosmic evolution. Telescopes can see back to shortly after the first galaxies formed. It's a story of continuous change, sparked by the Big Bang. But so far, the formation of the first galaxies, thought to be 500 million years later, has not been seen. Telescopes are yet to penetrate those cosmic dark ages. Here is as far as we get. We're zooming into apparently empty sky. But no, there are points of light beyond. The deeper we go, the farther back in time. It's a history of galaxies through the instruments of the Hubble Space Telescope, like drilling a core sample in a pinpoint of sky. Requiring 800 exposures, this is the deepest optical image ever obtained. Hubble reveals almost 10,000 galaxies. 100 of the smallest points are the most distant. Galaxies already formed 800 million years after the Big Bang. The oddest-shaped galaxies are from early times, when the universe was more chaotic. In contrast, closer and younger, this foreground spiral is rather ordinary. The universe has many mysteries, not least why it burst into life. This string of galaxies is another puzzle. Astronomers modeled it from 11 billion years ago. But how did such a massive structure develop so early? It defies our current understanding of cosmic evolution. Our galaxy, the Milky Way. Within its heart, most probably, a massive black hole. And surrounding, a spiral disk of more than 200 billion stars. A stellar throng which orbits the galactic center. One star is the Sun, with its family of planets 2/3 of the way out from the galactic center. Our perspective of the galaxy starts here, third rock from the Sun. This star and its two companions is our closest neighbor, Alpha Centauri, 4¼ light-years away. Next out is Barnard's star, a red dwarf, just under 6 light-years away. Sirius lies at 8.6 light-years. Light-year is the distance light travels in a year. From here, at Arcturus, light takes 37 years to reach us. Even at 300,000 kilometers a second, the light of these stars, Capella, is en route for 43 years. Castor, 52 light-years distance. 3 pairs of stars in mutual orbit. The double star Mizar with Alcor in the background, 59 light-years from Earth. At 95 light-years, Algol, a so-called eclipsing binary. Another, Beta Lyrae, 300 light-years away. They draw gas from each other, which spirals through space. Despite their great distances, those stars are our close neighbors in the vastness of the Milky Way. From Earth, we have an edge-on perspective. From beyond, we see the scale of our galaxy, some 20,000 light-years thick and 100,000 light-years wide. This galaxy, M83, is similar. In its spiral arms are patches of pink, where stars fire up. In our own galaxy, such a region is the Orion Nebula. Hot new stars cause surrounding gas to glow. Here are stellar nurseries, clouds of hydrogen gas collapsing under their own weight, pressure and temperature rising. When a cloud core gets hot enough, nuclear fusion triggers and a star is born. Another stellar incubator is in the Eagle Nebula, the famous Pillars of Creation. This column alone is 4 light-years high, a finger of dense molecular hydrogen bathed in the ultraviolet light of newborn stars. As that light slowly erodes the pillar, new stars are spawned from denser globules within. Starbirth generates stellar winds. In the Rosette Nebula, bright young stars are blowing the center clear. Here, new stars have blown a wind bubble 400 light-years across. Just one star, young, hot and windy, blew the Bubble Nebula. This dark swathe in Scorpius has been hollowed by newborn stars, blowing mighty winds. Clusters of older stars eventually clear their surroundings. Gas and dust are driven into the interstellar medium. The Pleiades are youngish stars, still ridding themselves of wispy nebulosity. Nebula means cloud. Stars are born of nebulae, from red dwarfs to supergiants. The more massive the star, the greater its hunger, and the shorter its life. Our Sun is an average star with a lifespan of 10 billion years. And it's not burning. Rather, at the core, a nuclear reactor is turning hydrogen into helium. With this key reaction at almost 15 million degrees Celsius, nuclear fusion releases 4 million tons of mass each second, energy that keeps the Sun shining. But one day, when hydrogen in the core runs out, the Sun will change color, like the orange-red star in this cluster. Here are several. They're called red giants. A red giant is a dying star. With core hydrogen spent, the star expands to at least 100 times its original size, puffing out envelopes of gas. The Helix Nebula is an example. Here are others. The rings are called planetary nebulae because, through a small telescope, they suggest planets around a star. In 5 billion years' time, it will be the fate of the Sun. As core hydrogen runs out, stability will be lost. The Sun will grow. First, Mercury will be consumed, then Venus. Deep within, helium will desperately fuse to carbon. Shells of gas will convulse into space. The Sun will be a red giant. Earth will probably survive, but as a cinder. Finally, as it blows off its outer layer, the Sun's collapsed core will be exposed. A dying ember, a white dwarf. A modest star like our Sun is long-lived compared to a more massive star. Here's the Sun in scale against a star with 3 times the mass. It starts, like the Sun, fusing hydrogen into helium. Then, when the hydrogen runs out, helium fuses into carbon. The reaction, at up to 100 million degrees, is the main source of energy in the fast and furious life of a giant. But this giant, like the Sun, will expire as a white dwarf. Only supergiants have a different ending. This one has 15 times the mass of the Sun. Again, like lower mass stars, the supergiant fuses hydrogen into helium. When hydrogen is gone, it's a smooth switch to fusing helium into carbon. Then carbon fuses into neon and magnesium. As they exhaust, on through heavier elements. At over 3 billion degrees, when iron is fused, the game is up. The explosion is a supernova. It can be as bright as a galaxy, a glowing expulsion of debris. Deep inside is a remnant beaming radiation. Compacted to less than 20 kilometers, a grain of it would weigh 1 million tons. The supergiant core has become a neutron star, a pulsar spinning many times a second. The Crab Nebula is a supernova relic. The flash that spewed it was observed by the Chinese in 1054. At the heart of the Crab, rings of material still emanate from its neutron star. Time-lapse by the Hubble Space Telescope. A graphic of the Crab's neutron star, jetting out material. It forms a surrounding ring, like a donut. Here, material from an ordinary star is drawn to a neutron star. Matter crashing to the surface creates superbursts. They expel more energy in 3 hours than the Sun in 100 years. Study of such explosions has revealed neutron stars that spin hundreds of times a second. Our galaxy teems with wonders, not least here in the Carina Nebula. We're approaching one of the largest known stars, Eta Carinae, perhaps 100 times more massive than the Sun. The star is already shedding material. A supernova waiting to happen. But this time, the colossal explosion will compress the core to beyond a neutron star, to a black hole. Supernovae are the lifeblood of our galaxy. Their debris and shock waves help create stars like the Sun. Their chemical elements are in every planet and every one of us. Our galaxy, the Milky Way, just one among the 50 billion galaxies believed to comprise the universe. This telescope hasn't been built, nor its location decided. But when it comes on stream, the sheer power of its vision could revolutionize our perception of the universe. Till then, the most powerful telescope is here. A desert mountaintop in Chile, South America. The 4 units of the Very Large Telescope. The VLT, as it's called, is carefully located beneath transparent skies to maximize its vision. Observatories need arid sites high above the clouds. The Canary and Hawaiian Islands are good because oceans steady the atmosphere. The less the shimmer, the sharper the image. The other vital factor is the darkest possible skies. That's why observatories are sited well away from the light and dust pollution of cities. As our planet lights up, good telescope sites are getting rarer. A telescope imitates the eye. Passing through the lens in front of the eye, the light from an external object is brought to focus at the back, on the retina. The image then passes to the brain for processing. Opening like a flower, this is the primary mirror of an astronomical telescope. It collects light like the lens of an eye. The mirror is mounted at the base of the telescope, which is not a tube but a sturdy framework, precisely aligning the optics. The Keck telescope on Hawaii. Instead of a single disc of glass, the primary mirror is a mosaic of 32 mirrors, all hexagon-shaped. They combine to form a 10-meter mirror. But how does a telescope work? Light from the cosmos is collected by the primary mirror, bounced to a secondary mirror, then back through a hole in the primary mirror to a focal point at the rear. That's the prime focus. Prime focus is always fixed behind the primary mirror. But there's another focal position. It's where light bounces from the primary to the secondary mirror, then to a third, and a focal point at the side. It's called the Naismith focus, and it's employed here. It allows the use of bigger and heavier instruments without skewing the balance of the telescope. The focal point is like the retina, and where the images are processed and the telescope controlled is the brain. A large modern telescope like Keck moves on a simple and relatively lightweight mount. Its drive is computerized, complex and fast. But an old telescope like this has a simple drive and a massive mount. The Anglo-Australian is the same, a huge equatorial mount in a very large dome. This is the most robust equatorial mount ever built. The last of its kind, the 5-meter Hale sits in a dome of 1,000 tons on Mount Palomar, California. But Keck, with a smaller dome and a mirror twice the size, trimmed and lightened telescope design. The nearby Gemini pushed farther with a dome that opens right around. This speeds the equalization of air temperature inside and out. Such atmospheric stability is essential in the pinpoint observation of the heavens. The Hubble Space Telescope has no such problems. Its 2.4-meter mirror orbits 600 kilometers overhead. Hubble images are superb. Freedom from atmospheric distortion more than compensates for the modest mirror. Hubble was launched in 1990 aboard Space Shuttle. Regular missions serviced and fixed Hubble and boosted its orbit. This mission was in 2002. The rendezvous went like this. Hubble is grappled into Shuttle's cargo bay. First, Hubble's solar panels, its power source, are rolled up like window blinds. They're to be replaced. Astronauts prepare new rigid panels. They'll be more efficient than the old, feeding the telescope additional electricity. Next, in the body of Hubble, a faulty power control unit is investigated. It's removed. And here's the replacement. Maneuvered into its compartment. Reconnections are with power tools and by hand. No easy task in gloves. Hubble gathers images with instruments behind its primary mirror. Incoming light is collected by the primary, bounced to a secondary, and back through an aperture to the instruments. The next task is to remove an old instrument, the faint object camera. Unloaded from cargo is the new ACS, the Advanced Camera for Surveys. It's installed in the vacant compartment. The final job is to replace a defective cooler on an instrument called NICMOS. NICMOS is the Near-Infrared Camera and Multi-Object Spectrometer. With a name like that, who can begrudge a cooler? Job done. And with mission complete, Hubble is carried to a higher orbit and floated into space. Just look at these images from NICMOS. And these from the ACS. And this, combined from the two instruments, of infant galaxies. But ground-based astronomy is fighting back. This 20-ton mirror is one of 4 cast for the VLT, the Very Large Telescope. 8.2 meters wide, 17 centimeters thick, ground and polished to an accuracy of 10 nanometers. And to keep their precise curvature, each mirror has 150 supports. Tiny computerized actuators that maintain the optimum shape of the reflecting surface. As each mirror slews when tracking the sky, the intelligent mirror supports compensate for shifting weight. The technique is called active optics. Another problem is the distortion of incoming light as it beams through our turbulent atmosphere. The result is blurred star images. The VLT has this solution: actuators beneath each secondary mirror. They sense distorted incoming light and deform the mirror surface to compensate. Wavy beams are straightened as if the air above the telescope were perfectly still. VLT images are pin-sharp. Previously, such definition was only achieved with a space instrument like Hubble. Compare these images of the same star. This is Hubble, and this the VLT. Thanks to adaptive optics, the VLT is delivering space-quality images from the ground. With the twin Keck telescopes on Hawaii, astronomers are now combining the light of both to produce the grasp of a much larger instrument. The VLT is going farther. It's marrying the light of the 4 big telescopes with that of 4 smaller instruments. Together, the grasp of a mirror over 16 meters wide. The eye of a giant. But this is a supergiant, OWL, the overwhelmingly large telescope. An eye on the sky 100 meters wide. OWL is an international project still in the planning. So vast, so ambitious, a suitable location has yet to be found. OWL will image planets around other stars. It'll see the birth of the earliest galaxies. OWL may be as important to science as Galileo's first telescope. How do we measure the universe? Astronomers describe it in light years, the distance light travels in a year. This galaxy, Andromeda, is 2.5 million light years away. Its light takes 2.5 million years to reach us. Our own galaxy, the Milky Way, is 100,000 light years wide. Just think of it. In 1 year, light travels 9.5 million kilometers. Such distances only make sense as light years. Our Sun, for instance, is 30,000 light years from the galactic center. But the first key in scaling the cosmos is closer to home. It's the diameter of Earth's orbit around the Sun, almost 300 million kilometers. The figure helps us calculate the distance to neighboring stars. So do their color and mass, plus their true intrinsic brightness compared with their apparent brightness. In Earth's orbit of the Sun, here's our view in January of a nearby star. As our orbit progresses, the star appears to shift in relation to the background stars much farther out. At the other side of our orbit, in July, the shift is quite measurable. By factoring in the shift and the diameter of Earth's orbit, simple trigonometry gives us the distance of the star. The technique is called stellar parallax. It works for stars out to several hundred light years, but that's far short of the whole galaxy and the halo of globular clusters that surround it. A globular cluster contains up to 1 million stars. They swarm towards the core 1,000 times closer than in our part of the galaxy, and they're ancient. The oldest could be 11 to 13 billion years old, predating the evolution of the main galaxy. The blue smudges are satellite galaxies of the Milky Way. Visible by naked eye from the southern hemisphere, they're the large and small Magellanic Clouds. Both are rich in young, highly luminous stars. This is the Large Magellanic Cloud, the LMC. Within it, in 1987, the death of a massive star. A supernova flash. In fact, the explosion was 160,000 years earlier, for the LMC is 160,000 light-years away. Here, the aftermath, the light echo of that supernova. The small Magellanic Cloud is more distant than the LMC. Both belong to our local group of galaxies. Other minor members are galaxy IC 5152, a dwarf galaxy called Leo 1, and NGC 6822, another dwarf. They all cluster around our own galaxy in the Magellanic Clouds. Others favor Andromeda, largest in our local group. A spiral like the Milky Way, Andromeda has almost twice our diameter. As we close with an arm of Andromeda, we search for a so-called standard candle. It's known as a Cepheid variable, a pulsing star that takes cosmic measurement beyond stellar parallax. The brightness of a Cepheid varies as it expands and contracts. This one, small and luminous, pulses fast. This one, bigger and more luminous, is slower. The speed is directly related to a Cepheid's true intrinsic brightness. By calibrating Cepheids in our local group, we get the distance of apparently fainter Cepheids deeper in space. They tell us M33, the Triangulum galaxy, is almost 3 million light-years away. Much deeper is the Sculptor group and the starburst galaxy NGC 55. A face-on spiral, NGC 300. They're at between 6 and 8 million light-years. So too the Silver Coin galaxy, NGC 253. Farther still, the M81 group, some 12 million light-years out. M81 is a face-on spiral. It interacts with its neighbor, the starburst galaxy M82, a firestorm of starbirth. Cepheid variables fix this galaxy, NGC 4945, at almost 13 million light-years. Beyond is Centaurus A, greatest galaxy in the Centaurus group. Centaurus A is 2 galaxies merged. Extending from 13 and 15 million light-years, the group includes M83, this beautiful spiral. At over twice the distance, a little group named Leo 1. The galaxy on the left is interacting with the others. More interaction. The Whirlpool galaxy and its partner at 37 million light-years. NGC 3198 at 47 million light-years. And at 52 million, M91, a barred spiral. Contrast it with this regular spiral, M100, slightly more distant. At about 55 million light-years, we've reached the Virgo cluster, heart of the supercluster that includes the Milky Way. Here are mighty elliptical galaxies, like M60 in the foreground. With 50 times more stars than our galaxy, this is the giant elliptical M87. Deeper still, the Fornax cluster at 60 million light-years contains this vivid barred spiral. But Cepheid variations can't be seen beyond this galaxy at 98 million light-years. A new standard candle is required. When a star exploded here, the galaxy's distance was known by Cepheid measurement, and it was the same here. Both galaxies are at 39 million light-years. The flashes were Type 1a supernovae, our new standard candle. They happen when a white dwarf draws matter from a red giant. When the dwarf reaches 1.4 times the mass of the Sun, the resulting detonation has a standard intrinsic brilliance. By calibrating Type 1a supernovae within the Cepheid range, we can measure the distance of such flashes 100 times beyond. They've confirmed that the galaxies of the Hydra Centaurus supercluster lie at between 150 and 160 light-years. The Coma cluster is at 320 million light-years, and the Hercules cluster at 500 million. This telescope at Mount Wilson, California, was once the largest in the world. In the late 1920s, it was used by the American Edwin Hubble to collect light from distant galaxies. He made a profound discovery. Hubble studied the light signatures of the galaxies, their spectra. They had many lines, and they were shifted in most galaxies toward the red end of the spectrum. It seemed that the fainter the galaxy, and presumably the farther away, the greater its redshift. Hubble realized it meant the universe was expanding, and it was space, not the galaxies, that was expanding, carrying the galaxies with it. As space expands, the light from the galaxies is stretched toward the red end of the spectrum. The farther the galaxy, the greater its redshift. Hubble's law. For galaxies lying beyond 1 billion light-years, redshift measures distance. It puts this galaxy cluster at 1.4 billion light-years, and this one at 2.2 billion. And this cluster at about 5 billion. Another cluster at 9 billion light-years. These images from the depths are by the aptly named Hubble Space Telescope. Viewed on Earth, this patch of sky is 1/10 the width of the Moon. As if looking through a drinking straw, we zoom into space and back in time. This is not animation. The images are by telescope, from the Hubble Ultra Deep Field. The farther out we go, the earlier we see. In this field, Hubble captured 10,000 galaxies. The faintest are from 13 billion years ago in an infant universe. Their distance and antiquity are measured by redshift. The cosmos in X-ray. Wavelengths that see what optical astronomy cannot. X-rays reveal the hotspots of the universe, gases around supermassive black holes, galaxies in collision, supernovae, stellar firestorms. By visible light, a supernova explosion. Now in X-ray, we see more of the expanding shell of gas. An apparently ordinary galaxy by visible light, but X-rays detect a titanic explosion. The galaxy Centaurus A, by visible light, unveiled in X-ray as two galaxies merged. An optical view of Stephan's quintet, a group of interacting galaxies. Superimposed X-ray shows blue streamers of scorching gas, product of the interaction. Visible or optical light comes in wavelengths our eyes can see. It's split into the 7 colours of the rainbow, determined by wavelength. Violet has the shortest wavelength, red the longest. But optical light is just the visible sliver in a band of invisible radiation called the electromagnetic spectrum. To the left, beyond violet, is ultraviolet radiation. Farther left are X-rays and the very shortest wavelengths, gamma rays. To the right, beyond red, infrared extends to the longest wavelengths of radio. All the human eye can see is visible light, a tiny fraction of all radiation. Starting here by visible light, M51, the Whirlpool galaxy. Now M51 in radio waves, the invisible made visible. Next, infrared, which highlights cool clouds of gas and dust. Ultraviolet radiation locates hot young stars. And finally, X-rays pinpoint the very hottest gases in M51. A laser show where smoke particles reflect and scatter light. In the atmosphere, dust and moisture cause similar scattering. It's a problem for invisible astronomy. With optical observation, mountaintop telescopes reduce such atmospheric distortion. It's the same with near-infrared. For above the clouds, there's no water vapor to scatter its radiation. Lower down, the only radiation to get through is visible light and radio waves. With the exception of near-infrared, where it's moisture-free, most of the electromagnetic spectrum is blocked by scattering and only detected in space. But the long waves of radio reach the ground. They're caught either in a big single dish like this steerable telescope at Parkes, Australia, or by a network of smaller dishes. Here in New Mexico, America's very large array. Each dish contributing to a collective focus, so-called aperture synthesis. A radio image of Tycho's supernova remnant. And here, radio galaxies. The jets indicate a supermassive black hole at the heart of each galaxy. An optical image of the Crab Nebula, remnant of an exploded star. Its superdense core, a pulsar, is revealed at the center by radio. Again optically, a calm group of galaxies. But in radio, no such thing. They're interacting, drawing material from each other. By visible light, an ordinary elliptical galaxy, M84. But no, radio reveals the jets of a supermassive black hole. Another elliptical galaxy, NGC 1316. Radio unveils vast bubbles of gas either side. To infrared astronomy, this is Spitzer, the coolest space telescope. Distant enough to avoid infrared from Earth and shielded from the sun, Spitzer is cooled to minus 270 degrees Celsius. Infrared astronomy probes dense clouds of dust and the cooler cosmos. See how Spitzer peers into this cloud in different wavelengths of infrared. Newborn stars appear. A pair in the head of the cloud have cleared a cavity. Optically, one star was brighter than the other. Now they're comparable. It implies a planetary disk around one star, penetrated by infrared. Starting again in visible light, Spitzer closes on a dark cloud, in different wavelengths of infrared. The cloud becomes translucent. Revealed are plumes of supersonic gas jetting from an embryonic star. With visible light, the Tarantula Nebula, unveiled in infrared as a cauldron of starbirth. A visible image of the galaxy M81. Spitzer, combining 3 wavelengths of infrared, highlights the spiral arms. Within them, in the longest wavelength, massive stars are forming, the bright spots. The sun emits all sorts of radiation, including the cause of sunburn, near ultraviolet. A little reaches the ground, but far ultraviolet, which is harmful, doesn't. So this far ultraviolet movie of the sun was from space, from a craft called SOHO. So was this in even farther ultraviolet, the seething solar atmosphere, the corona. And here, in farthest ultraviolet, we're higher and hotter in the corona. Clear of interference from Earth, this craft Galex images the cosmos in ultraviolet. During each orbit of Earth, Galex sweeps a strip across 1/8 of the sky. By visible light, the peculiar galaxy Centaurus A, Galex, in ultraviolet, sees great emissions from hot young stars. The Andromeda Galaxy by visible light, Galex shows where stars are forming. It's the same here, visible to ultraviolet, a galaxy in the Sculptor group. X-ray astronomy gets no better than the Chandra Observatory. X-rays are hard to collect. Head-on, a mirror just absorbs them. But Chandra's mirrors are like concentric barrels. X-rays graze the mirrors at shallow angles to be reflected and brought to a focus at an electronic detector. After a supernova, Chandra excels at imaging waves of expanding gas. They glow brightly in X-ray. This is Cassiopeia A, a supernova remnant recorded by Chandra. And here, the starburst galaxy M82. X-ray shows exploding stars, neutron stars, and black holes. The famous colliding galaxies, the antennae. As they interact, here by visible light, there's a firestorm of starbirth. But in X-ray, Chandra sees more. A maelstrom of exploding stars, neutron stars, black holes, and gas at 100 million degrees. There's a black hole in this galaxy, Perseus A. Revealed by Chandra, the white spot at the center is the clue. These ripples, produced by sound waves in hot gas around the galaxy, are an effect of matter jetting from near the black hole. The cosmos in optical light. And now, as though we could sense gamma rays and see the most powerful explosions in the universe, one such was detected by a space probe observing the sun. They're called gamma-ray bursters, and they average one a day across the sky. Hypernovae are thought to be the cause. An immensely massive supergiant runs out of fuel. The core collapses to a black hole. Powerful jets spew from the surrounding disk. They blast through the stellar surface. With a supermassive black hole inside, it's all over. A gamma-ray burster. The flash is as bright as 1,000,000 trillion suns, and only detected in gamma rays, the most energetic radiation in the electromagnetic spectrum. A binary star system, a blue supergiant and its hungry companion, a black hole. Relentlessly, a plume of gas is drawn from the hapless giant. The black hole is an object so collapsed that nothing escapes its voracious gravity, not even light. As material from the companion swirls inward on the accretion disk, as the event horizon is crossed, everything is trapped. Extremely massive stars are thought to generate black holes. In old age, as hydrogen runs out, the nuclear furnace at the core fuses heavier and heavier elements. In the end, with nothing left to fuse, the core becomes solid iron, and it collapses. The result is a catastrophic supernova, blasting the outer layers far and wide, and compressing the core still farther. Crucially, the collapse only becomes a stellar mass black hole if the original iron core had more than 3 times the mass of our Sun. Detecting a black hole is difficult because it's invisible and just a few kilometers across. The chances increase if the black hole is in a close binary system. Then, jets can be seen blasting at right angles from the swirl around the hole. For as it spirals inward, some material is saved at the brink, pitched into space by the shockwave around the central vortex. The motion of an orbiting companion allows us to weigh a black hole. Most have 10 times the mass of the Sun. At the heart of our galaxy is believed to lurk a massive black hole. It could be the case with most galaxies. But our galactic center is obscured by star clouds and dark nebulae, so there are no visual clues. X-rays, however, reveal hundreds of white dwarfs, neutron stars, and stellar mass black holes. Closer, and 2 vast lobes suggest a massive black hole dead center. It may look like this: incandescent flares jetting dozens of light years as matter falls on the accretion disk. Astronomers believe the suspected black hole at our galactic center may have the mass of 3 million suns. Andromeda, our nearest major galaxy, probably also has a black hole at its hub. But Andromeda's could have 70 million times the mass of our Sun, and be 2. A bright spot, a clue to the hole, is detected by telescope. Tighter still, and there are 2. Did Andromeda swallow a smaller galaxy? 5 times more distant, the strange galaxy, Centaurus A. It's crossed by a lane of dark dust. Astronomers think the cause was a gigantic collision, a dusty spiral galaxy scything into the original spherical galaxy. With visible light, there's no hint of a black hole. But radio shows vast lobes extending from the center. Add X-ray, and there's more structure. Look at the narrow blue jet, a spout of material heated to millions of degrees, shooting from a massive black hole. Animation shows what's happening. The jet is lucky matter hurled from the brink. The rest, the bright accretion disk, is doomed matter spinning towards oblivion. That pivotal black hole of Centaurus A is thought to have a mass of some 200 million suns. The heart of this nearby galaxy, NGC 4945, also has a black hole. It has the mass of 1.5 million suns. The one in galaxy M106 has 40 million times the mass of the Sun. This galaxy has a supermassive black hole of 1 billion solar masses. There's another in the Sombrero galaxy at 700 million times the mass of the Sun. Galaxies grow by merging, and so do massive black holes at their hearts. The antennae galaxies are examples of such a cosmic combination. At the center, the merger has sparked a great firestorm of starbirth. The maelstrom is revealed in X-ray. Exploding stars, neutron stars, searing gas, evidence of black holes. Animation of another galactic collision. Galaxies known as the mice because of their tails. Here they are by telescope. In simulation again, the mice are prime candidates for a binary black hole. As galaxies collide, their black holes fall quickly towards the hub of the merged galaxy. But instead of merging themselves, they orbit each other for hundreds of millions of years. When they do combine, they form a supermassive black hole, causing ripples in the fabric of space-time. An active galaxy usually signals a supermassive black hole. Radio reveals jets of energy expelled from the accretion disk of a supermassive in M84. By visible light, another example is Virgo A, M87. In different wavelengths, it's an intense radio source, especially the orange region. Optically obscure, a narrow jet shoots from the center. It's clear in radio, a stream of high-energy electrons, and by X-ray, accelerated pockets of scorching plasma. Animation shows the font of that energy is material in the accretion disk, spiraling into the black hole. With the mass of 3 billion suns, That void in M87 consumes the equivalent of several Earths every hour. So-called Seyferts are active galaxies with brilliant nuclei. This Seyfert is NGC 4151. Its energy is from the disk surrounding a supermassive black hole. NGC 1316 reveals much more in radio, orange-red billows suggesting a supermassive black hole. The same goes for 3C31 with jets of radio emission in red. The radio galaxy Perseus A. As visible light resolves into X-ray, the central white spot is the accretion disk of a supermassive black hole. From poles of the disk, jets blow cavities in the hot surrounding gas. As matter plunges to the event horizon, some shoots at right angles from the shockwave of the central vortex. Those jets create the cavities. Back now in X-ray, they're clearly visible in this image of Perseus A. A pair of galaxies, so-called radio galaxies, where supermassive black holes are the probable source of energy. Cygnus A is another. From its hub, material jets at close to the speed of light to create these lobes. Such emissions demonstrate the great engines of supermassive black holes. The most powerful black holes are at the heart of quasars. Quasars are the superluminous cores of otherwise normal galaxies. A radio map of the same quasar, over 2 billion light-years distant. This mighty jet shoots 150,000 light-years into space. Now in false color, an optical image. The quasar is known as 3C273. A supermassive black hole at the heart of a quasar. Its mass several billion times that of the Sun. Its event horizon as wide as the solar system. Quasars are the brightest objects in the universe. The largest powered by black holes weighing 10 billion suns. From the Hubble Space Telescope, images of quasars. They're so bright, the host galaxies are ghosts in the glare. Black holes powering quasars have enormous appetites. They gobble the equivalent of up to 40 Earths an hour. So what are quasars? They're thought to switch on when a supermassive black hole starts gorging on gas, dust and stars. Falling inward as an accretion disk, they emit prodigious radiation. The sphere of our cosmos, everything we know to exist in the universe, could be a dewdrop in an infinite mist. On strands of gossamer may be parallel universes. They would have time and space like us, but possibly different forms of matter. This idea is gaining credence among physicists. Already they've accepted that rather than 4 dimensions, there are 11. So the notion of one universe budding from another is not so wild. 11 dimensions may well accommodate a multiverse of endless universes. But until the theory is developed, it's science fiction. Another theory is a multiverse of bubbles, each bubble a universe floating freely and unconnected. But if 2 bubbles should touch, there's a cataclysmic explosion, a Big Bang. A new universe is born, meaning ours may not have been the first. Conventional thinking, however, sets our Big Bang as the start of everything. We know nothing of what may have gone before. 14 billion years ago, time and space began. So did radiation and matter in a furnace of generation. Subatomic particles made protons and neutrons. Atomic nuclei formed. Then the first elements. Electrons, here in blue, were captured in closed orbits around atomic nuclei. Atoms were created. 77% were hydrogen. 23% helium, plus traces of deuterium and lithium. As electrons were locked into atoms, they no longer blocked the passage of light-bearing photons. The universe became transparent. It was 350,000 years after the Big Bang, and the radiation released then is still detectable today. The colors are minute temperature differences. They indicate the earliest clumping of matter. The universe was taking shape. Gravity caused galaxies to cluster in filaments. Between them were ever-expanding voids. As matter condensed and heated, stars fired up. The universe was 200 million years old. But it took perhaps hundreds of millions of years of merging, coalescing, and evolution for the galaxies to shine and align as they are today. The early universe had nothing heavier than lithium. Only when massive stars formed was material like iron created. Exploding as supernovae, heavy elements that had been fused in the cores of superstars blasted into space. Those blasts forged even heavier elements, like uranium. Thus did supernovae seed the cosmos with 92 naturally occurring elements. Most of the matter that forms Earth originated not in the Big Bang, but in massive stars. The air that we breathe, the water in our oceans, trees, plants, all animal life, the fabric of our planet, mountains, rocks, and canyons, metals for manufacture and building. Everything around us consists of matter, matter made of atoms. But there's probably far more matter than meets the eye. Only 4% is ordinary matter, the rest is hidden, and it's thought to comprise the other 96% of the universe. Of that, most is mysterious dark energy, 73% of all there is. The remainder, 23%, is so-called dark matter. In the early universe, cosmologists believed dark matter was crucial. It would dominate gravity, dictating the way galaxies formed and how they clustered. There is much debate, but the likely scenario is that dark matter first caused galaxies to form, then galaxies to cluster, and eventually clusters to make superclusters. But what's the evidence for dark matter? Since it's invisible, it can only be detected by gravity. Dark matter could be affecting this galaxy, causing the outer parts to spin faster than visible matter justifies. A vast unseen halo is probably accelerating the galaxy. Dark matter most likely pervades all galaxies. Here, it's not to be confused with the opaque regions. They're just dark clouds of ordinary matter. Real dark matter is a powerful, invisible presence that tugs on every star in the galactic disk. Over thousands of years, as they orbit the galactic center, stars gently oscillate. The way they move up and down is modified by dark matter, for studies detect a lot more mass out there than can be seen. Some pull is due to dark interstellar dust and cosmic cinders like white dwarfs, neutron stars, and black holes. But dark matter outpulls them all. On a larger scale, galaxies within clusters orbit one another. Were it not for dark matter and its invisible mass, they wouldn't dance so close. The fact that galaxy clusters have been such stable structures through the history of the universe is due to the influence of dark matter. The great physicist Albert Einstein first demonstrated that light can be bent. His general theory of relativity shows that massive objects like the sun distort space-time and bend light. Put a massive object in the way, even if it's invisible, and the result is gravitational lensing. We can't see a black hole, but it bends passing light. The intervening object could just as well be a galaxy with lots of dark matter. From a galaxy far out in space, imagine a beam of light traveling to Earth. Put a massive cluster of galaxies in the way and they create a gravitational lens. Light from the distant galaxy is magnified, brightened, and distorted. The more massive the cluster in between, the greater the effects for the observer on Earth. Now, because the distribution of matter in the intervening cluster is uneven, light from the distant galaxy is smeared and curved into faint arcs. Scientists use the arcs to weigh dark matter and to work out its invisible distribution in the galaxy cluster. Although we see its effect, the nature of dark matter remains a mystery. Another effect of lensing is multiple images. One of the most spectacular is the so-called Einstein cross, a central galaxy framed by 4 images of another. It happens like this. Light from a quasar in a remote galaxy is lensed by an intervening galaxy with a supermassive black hole at its center. The quasar's image is bent and multiplied. On Earth, we get 4 images of the quasar with the lensing galaxy in the middle. Einstein's cross. Dark matter is crucial in determining the fate of the universe, as is the total amount of matter, so-called critical density. Since space is curved, there are 3 possibilities. The first is a closed universe. This has sufficient matter of all kinds for its gravity to eventually halt the expansion of the cosmos, the theory of the Big Crunch. Expansion would become contraction, the universe disappearing whence it came. The second possibility is a flat universe where space has a curvature of 0. In this theory, total matter is exactly the same as critical density. It means the universe has no bounds and will expand forever, but that expansion will get slower and slower. In infinite time, expansion would stop, but infinity by definition has no end. The third theory is the most likely. An open saddle shape where total matter is less than critical density. This universe expands forever, and it accelerates because of dark energy, an anti-gravity force. The radiation map of the early universe seems to confirm that dark energy is 73% of the cosmos, dark matter 23%, ordinary matter 4%. So what of the future? Stars will continue to form and shine for up to 100 trillion years. But inexorable expansion means our cosmos will become increasingly cold, dark, and lonely.